Okay, welcome back everyone to this tutorial video series on deterministic finite automata. So in the last video, we looked at some formal definitions of deterministic finite automata. Now we're actually going to look at our very first example of a such machine. So in this example here, I've created a deterministic finite automata M. And before I get to actually what L of M is, let me just look at it a bit more. Let's just look at it in terms of each of its components. So first of all, what's my start state? So my start state is going to be the state that has this incoming edge. Okay, so it has this unique incoming edge with no labels. So this is typically the way to refer or signal that Q0 is your start state. You can also write start if you want to be extra careful, right? So I'm just reminding us of the 5-tuple definition, okay? Okay, so that's what Q0 is. Now my set of states, right? Q is Q0, Q1, and Q2, right? So I have Q0, Q1, and Q2. Okay, so that's my set of states. My alphabet or my keyboard is 0, 1, right? So 0, 1, and whoops, this shouldn't be M, this should be my set of final states. My set of final states, the way I denote final states here is with this double circle. So the double circle here refers to a final state. So a DFA can have more than one final state. It could have no final state because my set of final states is a set, right? So it just so happens here that my set of final states is the set that contains Q2 only. Okay, but now the most interesting thing is actually my transition function delta. So remember, delta takes a state, takes a letter, and returns another state. So it tells you where to go. It tells you where to go, right? So where to go from Q while reading my letter sigma, right? So where to go from Q while reading sigma. Whoops, this should be prime. So, right, this is how you would read this graphically as this, and its functional form would just look like this, right? Okay, so what does this actually look like in my diagram here? So for instance, for my delta here, so I'm actually going to make a table. So let's say for Q0, right? Say I have a table Q0, and I read a 0 or a 1, where do I go? So if I'm at Q0 and I read a 1, then I go to Q2, right? So I go to Q2 upon reading 1. If I'm at Q0 and I read a 0, I go to Q1, right? And then the other two states is actually quite easy. So if I'm at Q1 and I read either a 0 or a 1, I just go back to Q1. Same thing for Q2. If I read either a 0 or a 1, I go back to Q2, right? So I can just write this in tabular form. Oh no, it doesn't reach. Oh, that's annoying. Okay, right, so Q2, if I read Q2, if I read a 0 or a 1, I go back to Q2, right? So that's how you would write this. If this was just written as a tabular form like this, then that's how you would convert this sort of this formal definition. You can convert this back to a state transition diagram. That's what this is, right? So this is a state transition diagram, okay? And actually, I just want to emphasize something that I emphasized in the previous video. So how I presented it in my previous video is that I said you had an input tape and you had a control unit, okay? And at that point in time, we didn't actually know what a control unit consisted of, but now you can actually see, if I just copy the machine from the previous slide, My control unit is just this state transition diagram, right? And so if it reads the string, let's say 101, then essentially what this means is that its pointer starts at the beginning of the string, and its computation starts at the start state, right? So it begins at Q0. So essentially, what it's going to do is it's going to ask itself, okay, I'm at Q0, and what I'm about to read is a 1, because 1 is on my pointer. 1 is the thing that I'm staring at. So now what do I need to do? What is delta telling me to do? Well, delta is telling me to go to Q2, because if I read a 1, I go to Q2. Okay? And this is the relation that I was talking about more in the previous slide in the previous video, sorry, with the high level representation. As I was transitioning through states, it's because I was following this delta transition function and reading from my input tape here. Okay, so I just wanted to sort of circle back and try to close this loop on why I kind of introduced that high level concept. Okay, so this is my machine. Okay, and now it seems as though I'm claiming that the language accepted by my machine, or the language recognized by M, which, remember, what is the language recognized by M? It's the language of strings, so of strings W, that when you feed W into your machine, it always returns an accept. So all of those strings that produce accepts when feeding it to your machine M. And so what the claim that's here is that the language recognized or accepted by M are the strings over the alphabet 0, 1, such that these strings start with a 1. So this is the claim. Is it true, right? And how do we know that this is true? Well, we're going to show this quite easily using the state transition diagram. So let's actually look at an input string. So let's take the same input string that I mentioned previously, 101. So 101 starts with a 1. And so in theory, it should be accepted by M. But I'm just trying to see if this is true, right? So I know that my computation begins at Q0, and I know that my pointer is going to start at 1, right? So what happens once I'm at Q0 and I read a 1, right? So once I'm at Q0 and I read a 1, I'm going to borrow this edge to transition from Q0 to Q2, right? So now I'm at Q2. I'm at Q2, and now what's going to happen is I'm going to read a 0. So at Q2, I'm going to read a 0, and so I'm going to borrow this transition from my transition function, which tells me that once I'm at Q2 and I read a 0, I go back to Q2. Then once I read my 0, my pointer goes to the next symbol on my input tape, and because it's a 1 and I'm at Q2, I'm going to use this transition to go from Q2 back to Q2. And because my machine has finished the input, right? My machine has finished reading the input, and it's ended in a final state, right? It's in a final state because of the double circle. Then my machine M accepts the string 101. And what you'll notice is that it wouldn't have mattered whatever had occurred after the 1, right? So once I read this first 1, and I go to Q2, I'm going to stay in an accept state forever, right? So really, it could have been 1 and then anything else, and my machine would have accepted it, okay? So it seems like then my machine accepts all the strings that start with 1, but does it accept anything else, right? So what would be this anything else? Well, what happens if my string starts with a 0 instead? Well, let's look at this case. So If instead I have an input like 0, 1, 0, so my input starts with a 0, then from Q0, what's going to happen is I'm going to borrow this transition from Q0 to Q1, right? So I'm reading a 0, and I'm going to borrow this transition to Q1, and now I've landed in Q1. And what you'll notice is that Q1 is kind of like this black hole of death, or this black hole of rejection, okay? Because whatever you do, whatever next string you're going to see, whatever next symbol you're going to see, you're going to remain in Q1. And because Q1 isn't a final state, you're never going to accept that string, right? So you're in Q1, and now let's say you see a 1, right? So you see a 1, then you borrow this transition from Q1 back to Q1. Then again, you go back to Q1, and now you see a 0, so you borrow this transition to go back to Q1. And so you finish in Q1, your computation M finishes in Q1, but because Q1 isn't a final state, M is going to reject it. And in fact, it wouldn't have mattered what the input string would have been, as long as it had started with a 0, right? As long as it had started with a 0, then it would have gone to Q1, and then it would have been trapped. So this is also known as a trap state or a dead state. Okay, the black hole of rejection is more something that I just came up with, but really, I think it showcases exactly what Q1 is doing. Is you read this 0 and you land in Q1, and then after that, whatever you do, you can't escape the rejection that your machine is going to give you. Okay, and so it appears based on this argument that any string that does start with a 1 is going to be accepted, right? It's going to go to Q2, and any string that doesn't start with a 1 is going to go to Q1. So one thing that I think is important to mention is the empty string. So what about the empty string lambda, right? So I've been using lambda. You could also use epsilon for the empty string. Well, if you read the empty string, right, it means that, what does that mean? That means that your input tape is empty. So what your machine does is that it says, okay, I'm going to start, and then it looks at its pointer and it sees that it has nothing to do, right? So if it sees that it has nothing to do, then it's just going to stay at Q0, right? It has no instruction to go to 1 or 0 because there's nothing on its tape, right? And so what it's going to do is it's just going to stay stuck at Q0 once it reads the empty string. And because Q0 also isn't an accept state, then the empty string is going to also be rejected. And so truly this is the machine M that accepts any string that starts with a 1. Because clearly the empty string doesn't start with a 1, it's empty. And anything that starts with a 0 doesn't start with a 1, and so it gets rejected, right? Okay, so that's how to walk through a DFA to see what does get accepted and what doesn't get accepted. Now, let's see, how would you actually build a machine that accepts a language? So I think one trick that I usually tell myself, and it's going to sound a bit silly, but the trick that I tell myself is, what would you do if you were at the machine's place, right? So put yourself in the machine's shoes and try to do this computation yourself. So you have to remember that you have a finite amount of memory, so you can't write down everything you've seen and sort of look back to it, okay? And so I think that putting yourself, sort of picturing yourself within a state and then thinking, oh, what if I see a 0, what if I see a 1, and then seeing what could happen and where you should go is one of the best ways of creating these DFAs. So I'll illustrate that in this example. So I want to create a DFA that accepts the language L, such that L is the set of strings that contains 0, 0 as a substring. So for instance, the shortest such string, or the smallest such string, is going to be 0, 0. It could also be 0, 0, 1 or 1, 0, 0. It cannot be 0, 1, 0, right? This is not a string that contains 0, 0 as a substring. A substring, remember, has to be a contiguous sequence, right? So 0, 0 as a substring means that the two zeros are there consecutively in the string. So let's try to use this trick of putting yourself in the shoes of the machine. So you know that, you're going to have to start at your start state, right? And now suppose that you saw 0, 0 as your input. Well, if you see 0, 0, then immediately you'd like to accept, right? So you're going to read this for 0. And so you're going to say, perhaps there's hope for another 0. And so if you do see another 0, right, then that means that you've seen two zeros in a row. And so if you see two zeros in a row, right, so if you read this 0 and then this 0, then you should immediately go to an accept state, right? So Q2 is going to be my accept state, okay? And now, essentially, all I need to do, all that's left for me to do, is to fill in the transitions for all of the other states, right? Because there's a given property for a DFA that because it's deterministic, if the alphabet over which the language is defined is, let's say, 0, 1, then each state in my machine M, right, has to have exactly, so for every state Q has exactly two transitions, one for 0 and one for the symbol 1, okay? And so really all I need to do here now is just to fill in the blanks. So if I'm at Q0 and I read two zeros in a row, I'm happy, right? I accept. Does it matter what else I see after that? So let's say I have 0, 0 and then 1, 0, 0, 1. Well, it doesn't matter, right? Because I already found my 0, 0. So no matter what I see after, I'm going to constantly be happy, right? So actually, once I'm at Q0, I'm just going to always stay at Q0. So if I see a 0, whoops, sorry about that. If I see a 0 or a 1, I'm going to stay in Q2, and I'm going to continuously accept, right? So this is, you can think of this as just being continuously accepting strings once the first 0, 0 is seen. Okay? So what about the other states? So what if you start at Q0, right? But what if the first thing that you read is a 1, right? So what if the first thing that you read is a 1? Then you don't budge, right? You don't budge because what you're doing is you're trying to look for that for that sequence of two zeros. So if you have two 1s, then all you're going to do is just stay at Q0 because you're in this limbo kind of waiting state, right? So here, this transition is just because you're waiting for the first 0 to appear. And if you see a 1 and then after that you see a 0, okay, then you should go to Q1, right? Because you've seen your first 0, right? So Q1 really is the state of seeing the first 0, right? That's responsible of seeing the first 0, right? So what happens if instead of seeing a 0, it sees a 1, right? So what happens if it sees a 1 here? well, then it has to start its search all over again, right? Because the fact that I have a 0 in between these two ones doesn't help me. I have to reset my whole search. And so what happens is if I'm at Q1, which is the state of seeing the first 0, if I see a 1, it negates what I just saw, right? And so I need to reset my search. So this transition here, let's use a different color. Let's use green. So this transition here is for resetting the search for 0, 0, right? And so altogether, this is my transition function, right? This is my transition function. I start at Q0. I can see as many ones as I want at the beginning. I don't really care, right? Once I see my first 0, up, I go to Q1, because now I'm hoping that actually this is my first 0 of 2. If it is, right, if I see another 0, right, then I go to Q2 and I accept. Otherwise, if I see a 0 and then immediately afterwards I see a 1, then that means I have to reset my search. So I reset my search and I go back to Q0, okay? And so you can see that this machine is indeed going to be the machine that accepts or recognizes the language L, okay? And so that's how you would create, using this trick of putting yourself in the DFA's shoes, this is how you would create a machine that accepts the language L. Okay? Excellent. And so that's all I wanted to cover with respect to creating machines. The next thing I want to do is talk about regular languages. So that's going to be in the next video, where I'm going to provide an interesting property of languages which are related to the fact that they're accepted by DFAs. Okay? All right, so I'll see you next time.